There we go. All right, so today's lesson is maximum likelihood estimation. It's one of two or three estimation approaches that I really want to expose you guys to, especially now that you've seen about 10 discrete and continuous distributions, more or less. And this is a technique where all of those distributions have one or more parameters. Poisson has lambda, normal has mu and sigma squared, beta has alpha and beta, gamma distribution has alpha and theta, or alpha and beta, depending on the book that you're looking at, and binomial has n and p. And so you may be faced with a scenario where you have an idea that a distribution is appropriate for your data set, but you don't know the appropriate value to use for the one or two parameters that model has. And so the scenario you're faced with is, well, is there a way to use the data in order to estimate what that parameter value should be? So that's what we're going to be tackling today and Thursday, is what methods could you use in order to do parameter estimation. And this first one is really, really popular. It's called maximum likelihood estimation, or MLE for short or abbreviated. And I kind of summarize the basic algorithms or steps that you should take when you actually do it. Practicing is really going to make it stand out a bit more. But first, you need to put together your likelihood function, which is just the product of all of your density values. And so you could see here that you are taking your f of x function, but you're evaluating it at x1 and x2, x3, x4. At every data value, you are evaluating that f function, and you're multiplying all those terms together. That's called your likelihood function. Theta, I'm using just for a general parameter notation. But again, theta would be lambda for Poisson, it would be P for Bernoulli, and so forth. So it's just a general parameter term. Once you have your likelihood, you want to maximize that likelihood. And so from this point on, it's really Calc 1. At least it was probably Calc 1 for you guys where it came up. When you want to maximize or minimize, you take the derivative, set equal to 0, and solve. The only difference here is that often it's actually going to be more advantageous to maximize the log likelihood rather than the likelihood. And so that's why in step 2, once you have your likelihood, take the natural log and make use of that. And you'll see that it often simplifies things. So once you get your natural likelihood, in step 3, you're using calculus concepts to maximize. So again, take the derivative, set equal to 0, solve for the parameter. And then step 4, once you have your MLE estimator, which is going to be a function, if you have data, use that data. And so you'll see what I mean as I progress through actual examples here. The last thing is just before the first example, it's good to know what unbiased means. And so unbiased from a statistical standpoint is when the expected value of your estimator gives you back the parameter that you are estimating. And so if that happens, so if this holds true, what I just highlighted in yellow, then theta hat would be said to be an unbiased estimator, which is a good thing. And so oftentimes your MLE is going to be unbiased, which is why this method is very attractive. All right, so let's go ahead and actually apply it so you can see it in action. So the first problem, it says let x1, 2, up through xn, so n values, be a random sample from an exponential theta distribution. Find the MLE estimate of theta. All right, so we've got exponential, which means that f of x theta And you might see it as f of x semicolon theta. You might see it as f of x given theta. Both forms are fine. So if you happen to have a preference, feel free to do that. And the exponential distribution, if you have it memorized, great. If you don't, feel free to look back at your table of distributions. This is your exponential distribution. And the support is x is from 0 to infinity. So it's greater than or equal to 0. So that's our PDF. The likelihood is going to be f of x1 times f of x2 times f of x3, 4, 5, up through f of xn. And so that is just the formula. I'm writing it out, but if you're comfortable with the product notation, then feel free to use that product sign that I had up above. And so this is 1 over theta e to the negative x1 over theta times 1 over theta e to the negative x2 over theta times, and you would do that over and over again until you get up to the f function evaluated xn, which is 1 over theta e to the negative x sub n over theta. So it's at this point where some students are a little better than others at seeing what to do. And if you could see it in advance, you're able to kind of jump to it, and I'm okay with that. I'm just writing it out to try to make it clearer here. And so I could see I've got a constant before all of these exponential terms, so 1 over theta, 1 over theta, 1 over theta, and that I have n of those 1 over thetas. So when I simplify, I have 1 over theta to the nth power. And then the exponential, I have a product of exponential terms, which means I could add the powers. And all the powers have the same denominator. So I have negative x1 plus x2 plus x3 up through plus xn all over theta. And this is our likelihood. Now, personally, I like to manipulate this a little bit more, and I'll continue so that you could see what my preference is. And if you like to do it, feel free to do it on your own too. So I could see I have a theta to the negative n, and then e to the negative, and I'm going to write that sum in this form. But then I'm going to also use a trick, and that trick is recalling that x bar, which is the sample mean, is the sum over n, which means that the sum of the data is equal to n times x bar. And over here, I have a sum of data. And so I am going to make that substitution of what the sum of the data is equal to, and I'm going to rewrite this likelihood as theta to the negative nth power e to the negative nx bar over theta. And that's where I would stop with the likelihood. And so in general, I try to get the likelihood as a function of a statistic. And even though the data are statistics, X bar is a really simple, concrete one. So if you're able to put it in terms of an X bar or an S squared, proportion, a single value instead of a summation or a product symbol, then I recommend trying to do that if you can. It's not always possible, but often it is, like in this example. All right, so now from here, I'm going to go to step 2, which is to obtain the log of the likelihood. And so that is that cursive L of theta function. This is the natural log of the capital L. And so here it's really advantageous to be familiar with and comfortable with the log properties or laws. And so log of a product is addition. So this is the natural log of theta to the negative n plus the natural log of e to the negative n x bar over theta. And then anyone see what the next manipulation should be?
Does the exponent become the coefficient?
Yes, so powers can be brought down outside of the natural log. And so here, that negative n comes out front. So we have negative n times the natural log of theta. And you're going to have plus the negative n x bar over theta, which is minus n x bar over theta times the natural log of e. What is the natural log of e?
1.
Yep, thank you. And so now we're ready for step 3, which is to apply calculus. And so we want to take the derivative. So this is d theta of L, the cursive L of theta. So taking the derivative with respect to theta, it's always going to be the derivative with respect to the parameter you want to estimate. Here, there's only one parameter, so using d instead of partial derivative is fine. And we've got negative n times the derivative of natural log of theta is 1 over theta, so we have negative n over theta. And then you've got a theta to the negative 1 in the second term. So derivative of that is going to have a negative 1 up front and a theta to the negative 2, which is plus n x bar over theta squared. And so this is our derivative. So after you take the derivative, you set it equal to 0. So we set this equal to 0. And then there's a number of things you can do. Personally, I think the easiest is to get rid of the denominator. And so I could see that if I multiply by theta squared, that's going to give me a negative n theta plus n x bar. So you're multiplying both sides by theta squared. Let me write, that looks too much like an x. So let me write that as times theta squared. And now we want to solve for theta. And so theta is going to be x bar. So the ends are going to cancel out and you just get theta is x bar. Now this is an estimate. And so it's here where I would put a hat on it to denote that the MLE estimator is x bar. And if you had data that supposedly the exponential distribution was appropriate for, you would take the average of that data and that would be the estimate for that theta value, according to the MLE, the maximum likelihood estimation approach. There are more examples. I want to continue forward, but any questions on the one example I've worked through so far? All right, I'm not seeing any questions appear, so maybe you guys are just waiting to see a little more, which is fine. It's only been one so far. So let's take a look at the second problem here. And it starts off similarly. Let x1, x2 through xn be a random sample from a geometric distribution. Find the maximum likelihood estimate of p. What's the geometric distribution? Anyone recall or happen to see it on the table? I don't remember if I put it on the table, but anyone recall the geometric distribution? Negative binomial through first success. And so what does that look like, Muku? Do you happen to recall? So geometric, you've got x minus 1 failures, and then your first success. And so you could view that as q to the x minus 1 times p. So that's what we're going to make use of. All right, so this is a PMF. So the probability of x with the parameter p is 1 minus p to the x minus 1 times p. So p is this unknown parameter that we want to figure out if we had data, how would we estimate a value for it? And our log or likelihood of p is going to be 1 minus p to the x1 minus 1 times p times 1 minus p to the x2 minus 1 times p times, and you do this over and over again until you get to the xnth value. And then you try to simplify. So we've got 1 minus p over and over again. So you add those powers. And so this is the sum of your xi's minus 1s times p to the nth power. So each of those probability mass functions or mass terms has a p times a p times a p times a p, and there's n of those p's. So that's p to the nth. And then I could see that distributing the summation in the first power is going to be 1 minus p to the sum of the xi's minus the sum of ones, but you're adding 1 over and over again n times, so that's going to be minus n. This summation does not include that n anymore. And you still have times p to n here. And then the last manipulation that I would do is converting that sum of x into nx bar. So that's going to be 1 minus p to the nx bar minus n. You can factor out the n. It may not make it easier later on, but it's fine to do. And this is the likelihood. The log likelihood is going to be nx bar minus n times the natural log of 1 minus p plus n times the natural log of p. Then, what do we want to do next? Take the derivative and set it to 0. Good job, Alvin. Yes, so we want the derivative with respect to p, because that's our parameter now. So we want d dp of this log likelihood. And so that's going to give us n x bar minus n over 1 minus p. And the derivative of 1 minus p is -1. So I'm going to put that negative sign out front, plus n over p. Set that equal to 0. Now I'm going to multiply this by the left and right sides by p1 minus p. Again, this isn't the only way to do it, but it's a trick that I like. So when I multiply the first fraction by p1 minus p, the 1 minus p's cancel. And so I've got negative p times n x bar minus n plus, when I multiply n over p by p1 minus p, the p's cancel, and I have n times 1 minus p. And when I multiply 0 by p times 1 minus p, that's still 0. And so it's now over here where I want to manipulate in order to solve for p. And let's see, we are going to get, this term will be an n minus np. So that means that we have negative p, and we've got n x bar minus n from the first term that I just wrote that underneath. And then from the minus np, I'm going to have a plus n because I factored out a negative p. So you could see the n's cancel out. And I still have the plus n that is not multiplied by any sort of p equals 0. Now I'm ready to solve. And so I'm going to bring this negative p term. No, I'll keep it on the left. We've got negative p times n x bar. I'm going to bring the n to the right and get negative n. When I divide by nx bar, we get 1 over x bar. And this is our MLE, so that is p hat. So in this case, interestingly, the estimator for this p is going to be 1 over x bar. What type of values can the geometric distribution have? What can x be? Zero to infinity, greater than 0. So let's take a look again. So you are looking for your first success. And so x could be 1, 2, 3 onwards. And so remember, those are the observation values that you can see. You can see a 1, a 1, a 1, 2, 1, 3, 3, 1, 5. You know, you're going to have these integer values. And when you average that, you're going to have a value greater than 1. When you do 1 divided by that larger than 1 number, you're going to have a fraction between 0 and 1. And remember that p is a proportion or a probability of whatever success is that you are looking at. And so it makes sense for that value to be between or equal to 0 and 1. And so it's going to work out, and it always will, but this is a conceptual way of recognizing that you're going to get a meaningful number for your estimator. So it's pretty neat to see that that actually works out. All right, so that was your second example. The third one actually has data, so you'll get to see it applied. And it says an experiment was conducted, which resulted in the following observations. So you've got 1, 2, 1, 3, 4, 4, 5, 5, 9, 6. That's your sample. If the data are assumed to come from a geometric distribution, what is the likely value for the parameter p? So this is great because in problem 2, we found that the MLE estimator for a geometric distribution is 1 over x bar. And so per problem 2, p hat is 1 over x bar. And x bar, in this case, we've got 1 plus 2 is 3, 4, 7, 11, 15, 25, that's 34, 40. So I have a sum of 40 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. And so I have 1 over 4 on the bottom, or 0.25 as our MLE estimate for the value for P. All right, so we've done 3. Any questions at this point? There are quite a few more, but we've done a number that if you have questions, feel free to ask them at this point.
Wait, for number 2,
Mm-hmm.
how did you get nx minus n?
That is, so that was going, are you good up to this power?
I think so. Wait, you're just following the equation, right? Wait, actually, I know you explained it, but I don't. You got rid of the 1.
I didn't get rid of it. This one, this is the sum of x's minus the sum of 1's. But we're adding 1 when I is 1 up through when I is n. And we're adding xi's when I is 1 up to xn. And so the sum of x, I showed earlier that that's nx bar. But then you've got 1 when I is 1, plus 1 when I is 2, plus 1 when I is 3, plus 1 when I is 4, all the way up to adding 1's up until I is n, which means that you are going to have n 1's. And so if you had 5 2's, then you have a total of 10, 5 times 2. Here you have n 1's, and so n times 1 is n. So that's where that second term came from. That's what you're asking about, Sydney, right?
Yeah, and then so it's it's x n times, then n of plus 1's.
What was that?
You have, so it just ends up being n
Yeah.
because you plus 1n times.
Yeah. Mm-hmm.
Okay, and then how did you get to nx minus x?
Nx bar minus n.
Yeah,
Well, the sum of x is nx bar.
is it just, what is
And
that?
you just seem to catch on that when you add a bunch of 1's n times, that's n. So you have nx bar minus n.
All right, and then you split the 1 minus p to the nx minus n and p to the n when you would put ln of that. You like added them instead.
Yeah, because one of the log laws is that the natural log of a times b
Yeah.
Natural
Oh,
log
okay.
of A plus B. And so you're going to need to really know these down pat. And those should have come up at least in Calc 1, maybe pre-calc or even earlier. I'm not really confident where, but this shouldn't be the first time that you're seeing these log laws. I'm not seeing any questions appearing on the chat screen, so I'm assuming so far so good. All right, well, let's look at the fourth one then. It says let x1 through xn be IID. Remember IID you saw in the MGF transformation handout, independent and identically distributed. In particular, they are Bernoulli P random variables. We want to know what is the MLE estimate of P when you have a sample that is given. It's just a collection of 0 ones, because remember, Bernoulli is either true, false. There's only 2 possibilities, 0 or 1. And so the first thing would be to actually get your MLE estimator before you plug in values. That's my preference. You can actually do values first, but I don't think it's an attractive path to take. So what is your PMF? Anyone recall or happen to see in front of them the PMF for a Bernoulli random variable?
Yeah, I think I have it.
Mm-hmm.
It is p to the x, and then parentheses 1 minus p, parenthesis, up to raised to the 1 minus x.
Good. So when x is 0, you get 1 minus p, and when x is 1, you get p. So it gives you probability of success p if you are in the group of interest, which is 1, and probability of success 1 minus, or failure 1 minus p if you are not in group 1. And so this is your PMF. I'm going to pause the video for a minute or so, because I want you guys at this point to see if you could put together your likelihood function. And so see if you could formulate that product and simplify it. So I'll give you a chance to try to do that step on your own. Okay, so that was a minute or so to just try to get your likelihood function. And I know a number of you did, which is great. So hopefully the process that you went through, whether you were able to see it in your mind's eye or not, was recognizing that the likelihood, again, is the product of your PMF in this case, because it's a discrete distribution, evaluated at every xi value. And in general, there's n of them. And we have a parameter p. And so you're going to have a p to the x1 times p to x2 times p all the way up through the xnth power. And there's also going to be 1 minus p to the 1 minus x1 power times a bunch of other 1 minus p's up to 1 minus the xnth power, which you could simplify as p to the sum of the x's times 1 minus p to the sum of 1 minus x's And in turn, the sum of x is nx bar. So you've got p to the nx bar times 1 minus p. And the sum of ones when you're adding that n times is n. And the sum of x is nx bar, which is what a number of you got. So that's great. So now, if you didn't already go ahead, take the likelihood or the log likelihood of this. So take the natural log, see if you could apply the log laws appropriately. And if you feel confident with that, then even go ahead and try to use Calc 1 concepts in order to find the maximum or minimum. Should be maximum though. So see if you can get your estimator, and I'll pause the recording again. All right, so just in case not everyone is confident with the log laws and how to apply them, I just want to go through that step so that everyone could continue with the calculus 1 type concepts. So does anyone feel that they got the log likelihood appropriately?
I got nx bar times ln of p plus quantity n minus nx bar times ln of parentheses 1 minus p.
That is perfect. So nx bar ln p plus the next power of n minus nx bar times the natural log of 1 minus p. All right, so
Faster
hopefully,
than typing it out.
right?
I just started saying it was faster than typing it out.
Yeah. And so hopefully everyone was able to get this. If not, you've got some time in order to freshen up and become stronger with your log laws. But at this point, I want you to take the derivative, set equal to 0, and try to solve for p. And I'll pause and give a little longer for that process. Okay, so I know a number of you finished the problem in its entirety, which is great. So let's progress so that hopefully if you didn't finish, you at least could see, you know, where you got up to and how much is correct. So we want the derivative with respect to p of the log likelihood. So L of p, which is going to give us nx bar over p minus n x bar over 1 minus p. You set that equal to 0, and then you solve. And again, there's more than one way to do this. I like multiplying by the common denominator. So multiplying by p 1 minus p is going to give us n x bar times 1 minus p minus n minus nx bar times p equals 0. When you expand or multiply through, we have an nx bar minus nx bar p minus np plus nx bar p equals 0. And I could see that nx bar p cancels out because you're adding and subtracting that. And then dividing by n leaves us with x bar minus p equals 0, which means that our estimate for p, or p hat, is x bar. And when you actually apply the data, when you add that data, you get 9. There's 15 values. 9 over 15 is 0.6. And so the actual value of your estimator for the MLE estimator for this P proportion, which again is a probability of success, so should be equal to or between 0 and 1, is 0.6, which seems reasonable.
I have several questions.
Mm-hmm.
Why are you subtracting them?
Where?
Like when you're taking the derivative.
You're talking about this sign?
Yeah.
What's the derivative of natural log of 1 minus p?
It's not just 1 minus p?
The derivative?
Wait, p's treated like a variable?
It has to be, because you're taking the derivative with respect to p. If it was a constant, it would just be 0. So
Okay.
p is treated like a variable. The derivative is 1 over 1 minus p, but then you need chain rule, and the derivative of 1 minus p is -1, which is where that negative sign comes from.
Okay. I don't know what you did after that. Like,
It did the same trick that I applied to all the previous problems. I multiplied by the common denominator of p1 minus p. And so multiplying the left side by p1 minus p, the nx bar over p has the p's cancel out. And so you're left with a 1 minus p times. And the n minus nx bar over 1 minus p, the 1 minus p terms cancel out. And that's going to be multiplied by p.
so you multiply by p times 1 minus p.
Yeah, that's my preference. It's not the only way to do this. You can add the n minus nx bar over 1 minus p to the right. You can multiply one side by p, the other by 1 minus p. Then you could add or subtract in order to get all the p's on one side. You know, like there's other ways that you may or may not be more familiar with doing, which is fine. I just think this is a faster route.
Okay. But you factored out the n, yeah?
Mm-hmm.
What do you do with the n? You just, oh, you divide it by n and that just
Yeah, so when you
disappears.
divide by n, every term has an n in it. So the left side, the n's disappear. And on the right, 0 divided by n is still 0.
Where'd you get the 9 and the 15?
Because we were given this data set. So how do you get an average?
Oh, like the mean?
Mm-hmm.
Are we talking like the xp of x, or adding all the terms and dividing by the number of terms?
That one. X bar is just the average. And so you add up all those zeros and ones. There happens to be 9 ones, so you'll get 9 for the sum, and there's 15 values. So that is your sum of x over n.
Okay,
All right.
thanks.
So the next problem is the first one where you actually have a distribution with more than one parameter. And so the process is the same. It's just because there's two unknowns, you're going to use a partial derivative notation instead of the non-partial. So instead of a d dx or d mu, you'll use partial derivative with respect to mu. And so you'll see that as I progress through this. So we've got x1 through xn coming from a normal mu sigma squared distribution. We want to determine the MLE estimates for both parameters, for mu and sigma squared. All right, so I didn't necessarily give myself enough space, so I'm going to do some of the groundwork on the far right over here. First thing is to jot down the PDF for a normal. Feel free to check me. I do believe that I list the normal distribution in that table of common distributions. And you should see this or something equivalent to it. I might have pulled the sigma squared out of the square root in the denominator and the coefficient. But since we're going to want an estimate for sigma squared, it's cleaner to keep it in its sigma squared form. But is anyone seeing anything different or missing? Nope. Okay, good. Thanks, Miku. All right, so I am just going to visualize this a little differently. Instead of having that fraction, I'm going to write it to a power form for the 1 over root 2 pi sigma squared. So that's going to be 2 pi to the negative 1/2 times sigma squared to the negative 1/2. I could have kept those together, but I know that these are equivalent, times e to the negative x minus mu squared over 2 sigma squared. And I do that because the likelihood's going to be cleaner, and so is our log likelihood, and therefore the derivative. And so not all of these are necessary steps, but it just makes it a little easier in the process later on. So the log likelihood, or sorry, the likelihood of mu sigma squared, because again, now there's two parameters, we have n x's. And so I know that this constant of 2 pi to the negative 1/2 is going to be multiplied over and over and over again n times. So that's going to be 2 pi to the negative n over 2. And I know the same thing will be true for sigma squared. That's going to be sigma squared to the negative n over 2. And at the exponential is going to be multiplied over and over again, so you add the powers. Now, the 2 sigma squared's constant, so I am going to view this as the sum, e to the negative sum of x minus mu squared divided by 2 sigma squared. So I pulled that 2 sigma squared outside of the summation. Because again, that summation is really just on x, because x really has the index I. Now we're ready for the log likelihood. So log likelihood is going to be negative n over 2 times the natural log of 2 pi minus n over 2 times the natural log of sigma squared minus the sum of x minus mu squared over 2 sigma squared. So this is our log likelihood. Now we're ready for, I think it was step 3 that I listed it, which is to take the derivative. But we have 2 parameters, so I'm going to do mu first. It's just a choice, it's not required, but it happens to be the easier one because it's in the numerator, where sigma squared is in at least one denominator. So let's do the partial derivative, delta u, or delta mu, of the log likelihood of mu sigma squared. So everything other than mu is treated like a constant, which means the negative n over 2 natural log of 2 pi, all those are constants, so that derivative is 0. Negative n over 2 times the natural log of sigma squared, there's no mu in there, so that is 0 as far as mu is concerned. And the third term does have a mu, but it's inside that quadratic form. So you're going to use chain rule. And so that chain rule is going to give us negative. You've got 2 times the sum of x minus mu. So I brought the 2 down. I subtracted 1 from the power, multiplying by the derivative of the inside. The derivative of mu, or negative mu, is -1 all over 2 sigma squared. And so I could see that a few things simplify. The 2's cancel. The minus signs, or negative, -1 becomes positive. And so what I'm actually left with is the sum of x minus mu over 2 sigma squared. And I want to set this equal to 0 and solve for mu. So you have to stay focused. We took the derivative, or the partial derivative, with respect to mu. So my goal is to solve for mu for this one so far.
So the 2's cancel, right? So
Mhm.
it's just sigma squared.
Oh, yes, thank you. Yeah, just sigma squared on the bottom now. So if you multiply, or intuitively, the only way that ratio is going to be 0 is the top is 0. And so this implies we want to know, when is the sum of x minus mu 0? And the sum of x minus mu is the sum of x minus the sum of mu's. The sum of x is nx bar, and mu is constant. So you're adding mu over and over and over again. We don't know its value, but we know it has some fixed value. And so this is n times mu, which means that our estimator, mu hat, is x bar. All right, so that's great. I mean, you've seen this estimator come up this way a number of times so far, 2 or 3 times, I think now, where the estimate is just simply the sample mean. So it's kind of neat in this case that the population mean is estimated by the sample mean, which seems to make sense, but it's nice that it actually works out. Now we still have the other parameter to estimate, which is sigma squared. So we're going to go through the same process again. We want the partial derivative with respect to sigma squared now of the log likelihood. So looking back, that first term is still constant because there's no sigma squared in it. The second term does have a natural log of sigma squared. Remember, we're taking the partial derivative of sigma squared. So that 2 in the power isn't something that you need to bring down. So it's essentially sigma squared to the first power that we have. So the derivative with respect to sigma squared is just going to be negative n over 2 times 1 over sigma squared, negative n over 2 times 1 over sigma squared. And then there's a sigma squared in the third term also, so that you could view as a sigma squared to the -1 power. And the derivative of that is going to be negative sigma squared to the -2 power. Or, so that negative with the negative up front becomes positive. We have sum of x minus mu squared over 2, and that sigma squared is now squared also, so this is sigma to the 4th. Right, again, you have a sigma squared to the -1, and when you take the derivative of this, you have negative sigma squared to the -2, which is -1 over sigma squared squared, which is where that sigma to the 4th came from. And this negative sign made this one positive. All right, so now we want to set this equal to 0 and solve for sigma squared. I see again, I want to multiply by a common denominator, so I'm going to multiply sigma to the fourth. So I multiply by sigma to the fourth. What I get is negative n over 2 sigma squared plus the sum of x minus mu squared over 2. I want to know, when is this going to be 0? If I multiply through by 0, or sorry, multiply through by 2, the 2's disappear on bottom. And I'm solving for sigma squared. And so that is going to give me that sigma squared is the sum of x minus mu squared over n. And this is an estimator, so I'm putting a hat on that. And so what's great is notice that this estimator, the MLE of the variance, depends on the mean, the population mean. And so that we would estimate with X bar, we just found that first. And so we know that that would be X bar. And so if we plug that in, you'd have the sum of X minus X bar squared over n. And that formula should look familiar, but it's a little different than one that you've actually been using. Does anyone recognize how it differs? What is one of the formulas that, if you had a list of data, you've used in order to compute variance?
The denominator is n minus 1.
Mm-hmm. Yeah, so what you actually use, the formula that you've seen that has a sum of x minus x bar squared on top, usually divides by n minus 1, but this one doesn't. So let's see whether that's good or bad. And that's essentially what number 6 is getting at. So we want to determine, are these estimators in number 5 unbiased or not? So let's start with mu, that's the easier path. And we want to show the expected value of the estimator ends up giving us the parameter it was estimating. So does this equal mu? That's what we want to show. So you start off with first principles. The expected value of mu hat is our estimator, but what we got for the estimator for mu hat is x bar. And according to the central limit theorem, the expected value of the sample mean, or the mean of x bar, its distribution is mu. And so that is unbiased, which again is a good thing. And now let's go through for trying to demonstrate whether sigma hat squared is unbiased or not. So we want the expected value of sigma hat squared. And we're hoping that this comes out to sigma squared. So that's what we're trying to see. Now this is the expected value of the sum of x minus, I'm going to write that just as mu squared over n. That's what we've got so far. Now remember that that mu is really estimated by x bar, so keep that in mind. But I need to give you some background info here, and that is that n minus 1 times s squared divided by sigma squared, that is a random variable that has a chi-square distribution of n minus 1 degrees of freedom. So it's important to keep that idea in mind. We're going to make use of this fact. All right, so how are we going to do that? Well, I remember that s squared is the sum of x minus x bar squared over n minus 1, which means that if I multiply both sides by n minus 1, I've got that the sum of, hold on, I'm losing my pen here. The sum of x minus x bar squared is n minus 1 times s squared, which means that I could rewrite this as the sum of x minus x bar squared over sigma squared. And that still has a chi-square n minus 1 degrees of freedom distribution. Now we have a sum of x minus x bar squared on top here. That is the expected value of the sum of x minus x bar squared. But what we don't have is that sigma squared on bottom. And so I could multiply the sigma squared on bottom, but in order to make it mathematically sound, I also have to multiply a sigma squared on top, which I can pull out because sigma squared is not random. So it could come out of the expected value. So can that n. So this is the same as sigma squared over n times the expected value of the sum of x minus x bar squared over sigma squared. Now remember that what I have inside this expected value is a chi-square n minus 1 degree distribution or random variable. And if you look at your table, you will see, you won't see the gamma, or you won't see the chi-square, but what you'll see is for gamma, that the expected value for a gamma distribution, remember expected value is mean, is alpha theta. But for chi-square, alpha is r over 2, and theta is 2, which means that the expected value or mean of a chi-square distribution is just the degrees of freedom. And the degrees of freedom, in our case, is n minus 1. And so that means that this is the sigma squared over n times n minus 1, or n minus 1 over n times sigma squared, which is not just sigma squared. Granted, as n gets larger, as you have more and more data, the limit of n minus 1 over n is 1, so it approaches sigma squared. But this is biased. This estimator is biased. Because the expected value of sigma hat squared didn't just give us sigma, or sigma squared, it gave us n minus 1 over n times sigma squared. So it's because of that that someone, when they figured this out, they said, well, how can I get an unbiased estimator? And the problem is that we have this n minus 1 over n multiplier. So someone said, well, let's multiply this by n over n minus 1. But what you do to one side, you have to do to the other. So when you multiply the n minus 1 over n times sigma squared by n minus 1, on the right, you get sigma squared. But on the left, which I'm going to write over here, you have n over n minus 1 times the expected value of the sum of x minus x bar squared over n. And this n over n minus 1 stuff is constant, so you could bring that inside the expected value. To get the expected value of the sum of x minus x bar squared over n minus 1. Which, I apologize, I'm not sure if it was Miku or Sydney or someone before pointed out that the denominator that you've been using is n minus 1, and this is s squared. And that's why, if you happen to have stat experience, that's why when you're computing a sample variance, you divide by n minus 1, because that is an unbiased estimator. It's not found as an MLE estimator. The MLE estimator is biased for variance. But recognizing how to adjust for that biasness, you're able to get an unbiased estimator like we just did. That's pretty cool. So if you ever wondered, why do we subtract 1 from n? Why don't we just divide by n? That's why. Questions?
Can you, for 5 and 6, can you show what you wrote on the side? Because I didn't get to copy all that.
Sure.
All right. Okay.
Just let me know when you got it.
You know, for that rightmost thing that you wrote about the sigma squared to the negative 1, so you can't just make that sigma squared or sigma to the negative 2 like immediately, and then it'd be sigma to the negative 3 when you take the derivative of it.
Right, because you're not taking the derivative of sigma. You're taking the derivative of sigma squared.
Okay.
So, and that's why, you know, I tried to emphasize that keep that sigma squared in that sigma squared form. And if you're ever faced with a scenario like that and it bugs you because you just have that power that you want to bring down, just change the sigma squared to q, you know, and take the derivative of q. And then remember to sub in sigma squared for q later on. Like if that power being in there is throwing you off because it feels awkward not to drop it and subtract 1, then just call it something else that doesn't have a power temporarily, and then substitute back in later on.
Okay. But then why at the end do you make it sigma to the 4th?
Because that's after I've actually taken derivatives. And so I could have kept it as a sigma squared squared, which would have been fine. But I know that having taken the derivative already, I'm not in danger of making a mistake at that point. And so that's why it's okay to actually multiply or square out at that point.
Okay,
But it would have worked out even if I kept it as sigma squared squared.
Okay, thank you.
Sydney, are you still copying?
I think I got it.
Okay. All right, so we are on number 7. There are a ton of examples for MLE. All right, your friend wants to gamble with you using a penny of his choice. Before agreeing to play, you ask to see the coin and you toss it 8 times. The results are 0, 1, 0, 1, 1, 1, 0, 1, where 0 means it was a tails and 1 means that it was a heads. Define the probability model for this scenario as if the coin is fair. Oh wait, nope, sorry. That's on the wrong line. Define the probability model for this scenario as what's in the table. So X can be 0 with probability 1 minus theta, and X can be 1 with probability theta. If the coin is fair, I should have put that on the next line. If the coin is fair, then the value of the parameter should be 0.5. So if it's a fair coin, theta should be 0.5, which means that it's a 50-50 chance for heads or tails. Use maximum likelihood estimation to determine a value for theta and thus whether the coin is biased or not. Okay, so we want our likelihood function. So in this case, I am going to consider the data that we have at hand. What I mean by that is x1 is 0, and so that probability is 1 minus theta. X2 is 1, so that's theta. X3 is 0, which is 1 minus theta. X4, 5, and 6 are 1, which is theta times theta times theta. So that's going to be theta cubed. X, what did I say, 4, 5, 6, 7 is 0, so that's 1 minus theta. And X8 is 1, which is theta. And so simplifying, I've got theta to the 3, 4, 5, theta to the 5th, and 1 minus theta to the 1, 2, 3, third power. And that is our likelihood function. This one isn't so bad taking the derivative at this point, but the log likelihood does make it a tad easier. And so over here, the log likelihood of theta is going to be 5 times the natural log of theta plus 3 times the natural log of 1 minus theta. And now we want to take the derivative with respect to theta. And so you get 5 over theta minus 3 over 1 minus theta. You set equal to 0. And then you manipulate in whatever method you prefer in order to solve for theta. So again, for me, I like multiplying by a common denominator, which in this case is theta times 1 minus theta. That's going to give me 5 times 1 minus theta minus 3 theta. So I'm going to get 5 minus 5 thetas minus 3 more thetas, which is 5 minus 8 thetas, or theta hat equals 5/8. Which you could convert into decimal form if you wanted. 5/8 is fine. And so that means that our estimate here is 5/8. And our estimate for the probability of tails would be 3/8. All right, so in this case, there wasn't necessarily a clear distribution. You could have worked with your Bernoulli distribution because that would be appropriate with only 2 possibilities. But it should have worked out the same regardless of which way you do it. And there's only one other example left. So let's take a look at that one. It says, consider a line of the form y hat equals m times x minus x bar plus b. The line is used to model a collection of xy paired data and should minimize the sum of squared residuals. Namely, it should minimize the sum of y minus y hats squared. And we want to use least squares to estimate m and b. I'm just trying to think why I have this problem on this handout. Yeah, you know what? I'm going to cross this one out. It's getting a little ahead of ourselves. It's not, I mean, there's some things similar, but you're not really getting a likelihood or anything. I must have forgotten to erase this from this handout. It's getting to the topic of regression, which we'll get to next week, I think, but it's just a little ahead, and it's not actually using a probability distribution nor a likelihood or log likelihood. So I don't want to confuse you with that one. So 8 is not relevant for this particular topic. So, and that's it. And so 7 MLE oriented problems. There is time, and I will move on to the next topic, but before I do that, I just want to see if anyone else has questions. Okay. So after I bombarded you with all of that, the next one is typically viewed as an easier approach. Not as popular because MLE is well known, it's often unbiased. So if you could do maximum likelihood estimation if you need to, that's the preferred approach. But the next approach is called the method of moments, or MOM for short. You don't have to call it MOM or MOM, but it's method of moments. And it's typically easier because you are going to be using moments in order to solve for your unknown parameters. And so a lot of times this is a back of the envelope type of approach, if you happen to be familiar with that phrase. And your first step is to set the first moment equal to the mean. And so the expected value of x, which is mu, you are going to set equal to the estimate of x bar. And so that's what I'm saying in step 1 here, is to set that first moment equal to x bar. Now, if you only have one moment or one parameter that you are estimating, then you're only using this first step pretty much. But if you have 2 parameters, you'll need to use step 2 also, which is to set the second moment, which is related to the variance, equal to sigma squared plus mu squared. And so if you're not sure where that came from, remember that you guys have experience with finding sigma squared as the second moment minus the first moment squared. But if we're solving for the second moment, that is going to be the expected value of x squared is sigma squared plus mu squared. And so that's where that comes from. You would use the first equation in order to solve for one parameter. You'd use both equations to solve for two parameters if you have that scenario, which we will have in this handout. I'll see if we get to it this lesson, but it'll come up. And if you had, for some reason, 3 parameters or more, then you'd use the third, the fourth, and the fifth moments. Typically 1 or 2 parameters are what you'd be faced with. All right, so let's look at problem 1 here. We have a collection of data, x1 through xn, that are from an exponential distribution, and we want to find the method of moments estimate of theta. So this is the same type of problem that we had first for the MLE. We just want the MOM estimate for it. So according to the method of moments, we want to estimate, let's see, we want the expected value. So mu is the expected value of x, and the expected value of x for an exponential distribution. Does someone have their table in front of them? I don't remember if it's theta or 1 over theta.
It's theta.
Theta, thank you. Is theta. And we want to set this equal to x bar according to step 1. And so that means that our estimator, and because this is method of moments, I'm not going to use a hat symbol, I'm going to use a tilde. Theta tilde is x bar. And that's it. It's just figure out your mean, which you have in the table for the most part, and you set that equal to x bar. And if there's any work to do to solve for it, then you would do that. In this case, the mean is theta, and theta is x bar. And so that's our answer. Let's take a look at number 2. Here we've got a geometric distribution, and we want to find the method of moments estimate of p. So this is a geometric with p as our parameter. So there's one unknown, so we want mu, which is the expected value of x, and the expected value of x for geometric is, who was that? Miku, was that you that gave me the exponential one?
For negative binomial, it's r over p.
R over p.
So it'd be the same, right?
R is 1 for the geometric. So this is 1 over p. And we want to set this equal to x bar, which means that when we solve for p, take the reciprocal of both sides, p tilde is 1 over x bar. All right, so this one required a little extra work, but the basic process is there. If it seems too easy, great, let it be easy. Don't make it harder than it has to be. In this case, method of moments, for the most part, isn't really hard. Let me just look back to see what our estimators were for MLE. So the exponential one, our MLE estimate was x bar, which we got for a method of moments, so matched there. For geometric, our MLE estimate was 1 over x bar, which is the same that we got with the method of moments. They don't always match, but so far they do. Let's continue. This is the gamma distribution. I don't think we had an MLE one of this, but you could always do it on the side. So we want to consider a random sample of n observations from a gamma alpha theta distribution and determine the method of moments estimates for the parameters alpha and theta. So here we have 2 parameters. So the mean is the expected value of x. And for the gamma distribution, I think that's alpha theta. Do I have confirmation on that one?
Yeah.
Thank you. And that is x bar, where we're setting it equal to x bar. For the second moment, E of x squared, this is, so let's see, the variance for the gamma distribution, I believe, is alpha theta squared, which means that the second moment is alpha theta squared plus alpha squared theta squared. So that's the mean squared. And we want to set this equal to sigma squared plus mu squared. Just in case you all didn't follow that. Let's see. All right, so if you're not sure where that alpha squared theta squared came from, that's the part of the second moment. The table that again is on the lemma shows that the variance of the gamma distribution is alpha times theta squared. Correct me if I'm wrong. Miku, do you see it in the table?
Yep.
Thank you. So alpha times theta squared, but that's the variance. I want the second moment. I know the variance is the second moment minus the first moment, but the first moment is alpha theta. And so when I square that, because I plug in for mu, and then I solve for E of x squared, that gives me alpha theta squared plus alpha squared theta squared. So that's how I got to that point. And so now I want to figure out estimates for alpha and theta. All right, that's our goal. And I am using v plus x bar squared. All right, so v plus x bar squared. So v is an estimate for sigma squared. It's just short for variance. It's also defined right here in case you missed it on top. So it's n minus 1 over n times s squared, which is the MLE estimator. So it's the biased version. All right, so we need to solve for alpha and theta. I am going to use a trick. I see that alpha theta is x bar. And so over here, alpha theta squared is alpha theta times theta. So alpha theta is x bar times the remaining theta. And over here, I have alpha theta quantity squared. So that's x bar squared. And this equals v plus x bar squared. Now the x bar squares cancel out in this case. And solving for theta, I get theta tilde is going to be v over x bar. So that's 1. And then using the first equation and solving for alpha, I get alpha tilde is x bar over theta tilde. And theta tilde again is v over x bar. So when you plug that in and simplify, you get x bar squared over v. And these are your method of moment estimators for alpha and theta. All right, so obviously the method of moments often is a bit faster. I don't want to rush too quickly. So after going through 3, any questions at this point about the method of moments approach? Tony, how are you feeling? Good, okay, just checking. All right, so then let's take a look at 4. So in 4, you've got n random variables from a distribution that is f of x equals theta x to the negative, or x to the theta minus 1 power, where x is between 0 and 1 and theta is some positive value. We want the method of moments estimator for theta. Now this is not a known distribution. It's not in your table. So the first challenge should be what? Perfect, Miku. Yeah, so we know the method of moments estimator for one parameter needs the mean, or the expected value of x. So we need to find that. So mu is the expected value of x, which, since this is a PDF, it's continuous. So this is the integral from 0 to 1 of theta x to the theta minus 1 power dx. And you're multiplying x in there. So that's just part of the definition of the expected value of x is the integral of x times the PDF, which is the integral from 0 to 1 of theta times x to the theta dx. And this is just a polynomial. Remember that your variable that you are integrating with respect to is x. So theta is some unknown constant. And so this is the power rule for integration, which is theta over theta plus 1 times x to theta plus 1, which is being evaluated from 0 to 1. So when x is 1, this is 1 to some power, which is just 1, minus 0 to some power, which is 0, which leaves us with just theta over theta plus 1. That is our mean. Now the method of moments estimator says we want to set this equal to x bar and solve for theta. So that's what we're going to do. So multiply both sides by theta plus 1, and we get theta equals theta x bar plus 1 times x bar. Get the thetas on the same side, and so I'm going to subtract the theta x bar to the left and factor out a theta, so it's going to give me theta times 1 minus x bar equals x bar. And finally, solving for theta, which is theta tilde, is going to be x bar over 1 minus x bar. And being that x is between 0 and 1, theta tilde will always be positive, which is good because that's one of the constraints on theta. All right, so
Sorry, can you explain what you did after you had x bar or something? Like the second line?
I solve for theta. So what would you do to solve for theta there?
You have to look back at the steps or something?
No, once you get to this point, Sydney, if I had paused the video and said solve for theta, what would you do?
Oh, you multiply x bar by the denominator.
Okay, so that gets you here. And then what?
Oh, wait. Oh, okay. I think I get it.
You see it? All right. All right, so I am going to pause the video here for number 5, because I think many, if not most of you, hopefully, are ready to try to tackle this one on your own. Again, with the method of moments approach, don't flip-flop between the two methods. And so here you've got n observations that are binomial distributed. N is your general sample size, so it's not random, but P is what you want to estimate. And you want to estimate it using the method of moments approach. And so if you do this right, you should get this in 15 seconds or so. So I'm going to pause and I'll give you 30 seconds to a minute and see if you are able to get at your answer. Okay, so let's return to number 5 here. I know at least a couple of you got it, hopefully more. And again, with one parameter estimate, we're starting from, we want mu, which by definition is the expected value of x. And for a binomial random variable, we know, or you could look up in the table, is given by n times p. And that we're going to say is equal to x bar. And so we want to solve for p. And so the method of moments estimator after dividing by n is x bar over n. Pretty cool. Yeah, my PhD advisor would, you know, it was a statistics PhD, but we were kind of numerical analysts at heart, he and I. And so in my thesis research, a lot of times he'd come back and he'd be like, you know, I did a back of the envelope calculation and the estimator should be close to this. And he would use method of moments for his initial attack. And then we'd investigate the harder but more respected MLE approach. And so it is useful and often matches your MLE approach. And obviously, hopefully many of you find it much easier. All right, number 6. And wow, yeah, this is the last one on this handout. Consider a random variable where x1 through xn come from a uniform distribution. That uniform spans theta minus 1 to theta plus 1. And we want a method of moments estimate for the parameter. That should say theta, not p. Are you guys still seeing me? Hello?
Hi.
Okay, good. Just
Yes.
checking. Yeah, because my screen for some reason told me that I was signed out, so I got a little nervous. All right, so this again, this p should actually be theta. So that's what we want a method of moments estimator for. All right, so mu is the expected value of x. And for the uniform distribution, what is the mean of a uniform distribution? Anyone happen to remember? I believe it's halfway between your two values. Yeah, Miku and Tony, you both wrote it. Tony, be careful, use your parentheses. I know what you mean. And so we've got theta minus 1 plus theta plus 1. And we want to average those because that is the mean of a uniform. So this is going to be 2 theta plus 0 over 2, or theta. And as the first moment, you set that equal to x bar. And we have that our MOM estimate is just X bar, the sample mean. So in part B, it asks, what is the value of the estimate based on if we had made the observations of 6.61 up through 7.26? So what are you going to do? How do you answer part B? Yeah, thanks, Tony. Yeah, so we want the actual value of theta tilde, which we just derived to be X bar, and now we want X bar of those 5 observations. So go ahead and compute the mean. And I'll do that too. And did anyone happen to get a value? Thank you, Aaron and Miku and Tony. So yeah, I am getting 7.382. So that would be, based on this sample of 5, that would be our estimate for the parameter theta using the method of moments version. Now part C is asking for us to compute the variance of this estimator. So it's an estimate, which means that there's some variability, and this is the first time we're actually being asked to investigate that variability. So it's a measure of how accurate that estimator is. And we're actually able to do this. So the variance of theta tilde is the same as the variance of X bar, because that's what theta tilde is. And when you see an X bar, you should think of the central limit theorem, which says that X bar is normally distributed with mean mu and variance sigma squared over n. And so now in our case, we want to estimate this. We don't have the population, but an estimate for sigma squared would be s squared. And n is 5 observations. I realize my s and my 5 look similar. Hopefully that makes it stand out. And so now we want the sample variance for that data set. If you're able to get it quickly, great. I'll do it on the side and let you know what I get.
Is there a difference between when they say ask for estimate and estimator?
So estimator is usually just the functional form of the parameter. So theta hat, theta tilde, those are your estimators. But then when you actually get a value, that is an estimate of the parameter that you're estimating.
It seemed like you kind of solved it very similar.
And okay, so for variance, I am getting 0.45752. And after dividing by 5, I get about 0.0915. So this is a measure of the accuracy. It's the variability in the estimator. And so you could think of what we did with confidence intervals. We have a measure of the error of this estimate. We have the estimator itself. So even though we got a value of 7.382, you could think of we are 95% confident that theta, so I'm going a little bit beyond C here, but we are 95% confident that theta is going to be somewhere between our theta tilde minus 2 times the variance of theta, or sorry, standard deviation, and theta tilde plus 2 times the standard deviation of our estimator. That 2 is an approximation. You probably more likely remember the value of 1.96 when you're using the Z table is more commonly the value, but 2 is a quick approximation. So for 95% confidence, if you want to be really exact, you'd use 1.96. It's kind of common to approximate with just 2. So that's where that 2 number is coming from. And so if you actually plug in theta tilde and the variance value in here, what you'd get is 6.777 for the lower bound and 7.987 for your upper bound. And so the variability is actually pretty small, which is good. That means the estimator is pretty accurate. But if you wanted an idea of the range of values that parameter most likely is, it's somewhere between the 6.777 and 7.987. So in practice, if you were doing some sort of research and 7.382 wasn't quite working out well, you could investigate different values within this interval and look at some sort of curve if you had an idea of what the curve or distribution should look like in order to converge on, okay, here is the best value matching my expectations. And so that would be how you might apply something like this. All right, so we've gone through, I know I'm a few minutes over, but just to summarize, we've gone through 2 approaches to estimating parameters for distributions. Maximum likelihood is the more well-respected and known one, oftentimes yielding unbiased estimators, not always, but often. A method of moments is the easier approach, sometimes with unbiased, sometimes not, but it's quick and easy, and that's the attractiveness of that one. But for both of them, you often, especially if your estimator is just X bar, you could often use the central limit theorem in order to come back with an estimate for the accuracy or the variability of your estimator. And so that's what I expect you to be able to do. Things like what we've just done throughout these 13 problems that we did between these 2 handouts. There's one other estimating approach that I'll get to on Thursday, and then we'll do regression analysis. And it does seem like we'll have another class or 2 in order to cover some of the topics that I've skipped. So I'll decide which, if any of those to do, but so far we're at a healthy pace. I did post the next assignment, estimation 1. Estimation 2 won't be on there. I'm going to post another worksheet, and the reason is I'm just not finding good problems on MLE and MOM and estimation in general on web work, and so I'm just going to give you some of my own problems on the side. So there's only 1 web work left that I've created. I'll look into regression. Maybe I'll throw in some problems there in regression. But we're just about done with web work. Maybe 1, 2 more assignments. That's it. With that, thank you for giving me just 5 more minutes over my midnight, and I'll hang around just for a few minutes, because it is late on my end. And I'll stop the recording and I'll tackle any questions that you may have.